the things I'm going to present. They are joint work with Vitor Barros Nascimento, who should be here or he will be here at some point, and with Elaine, who is here. This is some work that we have been developing for the past year, I think. So this has been like a main focus on my PhD. So the title kind of gives away what I'm going to do today. So I'm going to talk a bit about bilateralism, and I'm going to talk a bit about base extension semantics, so a strand of proof-theoretic semantics. And we are going to analyze in the second part of the talk, we are going to see a particular kind of bilateralism, I guess, where we have incompatibility between proofs and refutations. So I tried to make this talk very high level and approachable for everyone. So I hope I managed to give a good talk to you guys. Feel free to interrupt if you need. And yeah, I mean, let's jump right into it. Okay, so first I need to understand how to use my computer. Okay, good. So an introduction. For the time being, I just want to give you like a very tiny grasp of what bilateralism is. I am, of course, no expert in the subject, but I managed to find a cool picture that I think illustrates what I want to tell you guys. So let's start by talking about proofs. So I guess that for the people that are here, proofs are one of the main concepts of our research, like in some way or another. But we all know, of course, that the meaning of proof, or what can be, what is a valid proof, is not something that is agreed by everyone. So this is a central point of disagreement, for instance, between classical and intuitionistic logicians, as they do not agree on the very nature of logical proofs. So you can see this picture that I have here. There is this man on the left that says, okay, so I have disproven this conjecture. And the man on the right goes, okay, so cool, that's nice. But you have a counterexample. And the one on the left, and he seems very pleased with what he's saying. He just goes like, no, no problem, right? I don't have a counterexample, but no. And the one on the right is very puzzled. So this kind of illustrates this disagreement between different notions of what may be regarded as a proof. And I mean, these differences, of course, reflect deeper disagreements about how we justify assertion and rejection in reasoning. And in here lies like a key aspect of what I'm going to talk to you about. And so I want to start by giving you like a classical account of assertion and rejection, and also about negation. And this account is the traditional Fregean account of negation, in which he depicts the denial or rejection of a proposition as the mere assertion of its opposite. And so Frege writes, to each thought there corresponds an opposite, so that rejecting one of them coincides with accepting the other. And we can jump to the last bit of this quote, which is the part that I want to call your attention to. He says that there is no need of a special sign for rejecting a thought. We only need a special sign for negation. So for Frege, rejecting something would be the same as asserting the negation of this thought. And this, in particular, it means that assertion and denial are essentially the same speech act. We just need to have this negation symbol to coordinate the whole thing. But this is, of course, not agreed upon by everyone. And in particular, this view has been challenged by contemporary logicians, which led to the creation of what we can now call logical bilateralism. So the key aspect here, according to bilateralists, is that these two concepts that I just mentioned, so assertion and rejection, are actually completely distinct speech acts, and we cannot reduce them to each other, right? So this idea that we do not need a special sign for rejection is not accepted at all. So it's completely rejected by bilateralists. And so in this philosophical strand, we also think that a proper account of logic should actually distinguish between conditions for propositional assertion and for propositional rejection. So this is all that I need to tell you about bilateralism. This is it's very quick overview, something like bilateralism in a nutshell, but I think it's enough to get started. Okay, so what's our actual starting point? So the logic that was our starting point in the beginning of these works that I'm going to tell you about today was the bilateral bi-intuitionistic logic to int, which Wansing describes. So we have the usual connectives. We also have co-implication, so all the intuitionistic connectives plus co-implication. And there is a natural deduction system for this logic, which is n to int. But in our case, we are going to use a slight adaptation of this system, which is n to int star. So they are deductively equivalent. And now I don't want to tell you much about what these rules or the specifications of these rules, but I just want to let you know that in Wansing system, some rules end with a line, can be a single line as we have in this rule here. And in our formulation of the system, we are going to substitute it by a dashed line, which I will tell you about in a bit. So we just modify a few rules and we get a deductively equivalent natural deduction system. And what we gain here, we can recover some properties that n to int apparently does not have due to the way that rules work coordinated with the operators. For instance, it is important for the subformula property. Okay, so starting point, logic to int and natural deduction system n to int star. And something kind of natural is that because in our setting, we are in a bilateral setting, proofs and refutations are seen as independent notions, our system will have to describe this in some way. So we have two kinds of rules, proof rules and refutation rules, and also two kinds of assumptions. So I will quickly go through the rules. So these ones are shared with intuitionistic logic. There is some notation here that I want to tell you about, but it's clearer in the next slides. So these are not surprising at all. So I will just jump over them. If anyone then wants to go back, let me know, but let's go to this slide. So I want to call your attention for some things. So for instance, first rule here, you can see that we have two kinds of assumptions, as I was just mentioning, and these are separated by this comma. And so the one on the left, I'm going to refer to as a proof assumption, the gamma, and the delta I will refer to as a contra assumption or a refutation assumption, something with like a negative emphasis. We also have a look at the introduction of the co-implication, for instance. We also have single lines, as the one I highlighted in green, which stand for proofs. And then we have double lines, which stand for refutations. We can also have the dashed line that I was telling you about earlier, highlighted in blue. And this basically means that we have two versions of the rule, one where every instance of the dashed line is substituted by a single line, and another instance where everything is substituted by a double line. Lastly, still about notation, for discharge assumptions, we have these single brackets in yellow, still in the rule with a dashed line. We have these single brackets in yellow for discharged proof assumptions. And let me go to the next slide. We have these double brackets for discharged contra assumptions. So the rules themselves, they are very similar to the rules of intuitionistic logic because this is just a dual bi-intuitionistic logic. So it is nothing very out of the box in that sense. But we do have these bits of notation that really help us mimicking the spirit of bilateralism in here. And so in Wansing system, for instance, this junction elimination was just one rule with single lines only, but we did this modification to get better proof-theoretical properties. Okay, some additional refutation rules. And yeah, okay, I think I can go here. So still on the introduction, last slide here, what is the aim of the talk? So the aim of the talk is for me to tell you about some recent developments in bilateral proof-theoretic semantics, in particular in bilateral base extension semantics. So the work that I'm talking about today is actually very recent. So this talks about basically 2 papers. One of them has been out like a preprint version since May, and the other one is online since like mid-October. And yeah, so for the first part of the talk, I'm just going to tell you about how to extend base extension to the bilateral setting. And then I'm going to talk to you about a particular like kind of bilateralism, that one with incompatible proofs and refutations. So in this second part, we refine what we did in the first part and try to analyze some things more related to actual mathematical reasoning, where, as you know, proofs and refutations or coexistence of proofs and refutations is not something that we actually design. Yeah, so this is it. Before going to these 2 things, I'm just going to quickly run through another very quick introduction to base extension semantics, as I am not completely sure of everyone's background here, but this will be like something very, very simple, just to introduce you to some clauses and how the thing works. Okay, so as I just mentioned, base extension semantics is actually a strand of proof-theoretic semantics. If you have seen talks from our like UCL group, you have seen that we have been working a lot with this kind of semantics. And what do I need to tell you about these? These are just like 3 slides. One of them is like an example, so it's really, really high level now. So what do I need to define here? Firstly, I need to tell you that, okay, it's base extension semantics because we are working with something that's called bases. And the objects inside these bases are called atomic rules, which are natural deduction rules where only atoms may show up. So we have this schema of a natural deduction rule, and we have as assumptions some sets of atoms, and then we can only conclude also atoms. And so a base is nothing but a particular collection of inferences about material facts. This expression here, material facts, so these are atomic propositions, but it's important to mention that these are material facts in the sense that bases are not closed under substitution. In the example that I will show next, it becomes a bit clearer why this is relevant for the relations that we want to define later. We define a derivability relation between atoms and sets of atoms. This is so you can think of this as the usual derivability notion in natural deduction, except that we restrict the rules that we can use to the rules in the bases. So basis sets of rules, derivability in this context is restricted to the rules pertaining in the basis. And well, it's called base extension, so we need to define what is an extension of a base, and it's just like the set theoretical notion of inclusion. So an atomic base C extends atomic base B if and only if it contains or is equal to base B. So these are the basic definitions. Let's just look at this example here. Consider this set B, a base, with these 3 rules. So for instance, rule 1 tells us that we can conclude Q from the atom P. We can also conclude S from Q and R, etc. And so we can see that we can build this derivation that I have here using first rule 1. So we assume P and we conclude Q. Then we assume R and we apply rule 2 to conclude S. And then by rule 3, discharging R, we conclude T. So there is a derivation in this base B showing T from B. Okay, but for instance, there is no derivation in B that we can use to show, to derive S from the atom R. And yeah, okay, so this is basically how it works. Again, if the bases were closed under substitution, maybe this last statement that I have here would not work as such, but we really can only use the specific rules and the specific atoms in the rules in the bases. So these are not rule schemas, they are actual, they are concrete in a sense. Okay, and a very well-known example that I will let you know about. So Thor Sandqvist proposed, I think it was in 2013, in a paper of his, a base extension semantics for IPL. So I will talk about a bit about the clauses here, because then in the bilateral setting, they get very heavy with notation. And so it's nicer for me to call your attention to some things here, and then it will work in a very similar way, but then we can just go through more swiftly. So let me call your attention to the first clause. So here we are defining a support relation in the basis. And in the base case, we have that the support of an atom is equivalent to the derivability of this atom. We also have the support relation for bottom defined in terms of support of every atom. So sort of explosion here. But something interesting, because if you look at clauses 3 and 4, I mean, they just look like the introduction rules for these connectives in natural deduction. So support of a conjunction is the conjunction of the support of the conjuncts. But for instance, if you look at clause 5, and we as in people who do base extension semantics, we will always talk about the clause of the disjunction clause. So you can see that this one seems very different from the others. And the thing is that here in the disjunction, we do not, we need to use something based on the elimination rule for this connective. So for the other connectives, we may use the introduction rules to define the clauses, but disjunction is actually not the same. And it has been shown that there would be like implications for completeness, for instance. So this is a key fact. And in the bilateral setting, we will still have something very similar to this in our semantics. Okay, so this is my base extension in a nutshell. And now I can go to actually talk about our work. So the first work that we did, the extension of bilateralism of the extension of base extension semantics to the bilateral framework. So how did we do this? Well, it makes sense that since bases are a collection of atomic rules, and now we have natural deduction rules with different kinds of flavors, so proof flavor and refutation flavor, it is natural that we also do this adaptation for bases, right? So now instead of just having like one kind of natural deduction rule, we have two kinds, which we will call proof rules and refutation rules. So the notation here is exactly the same as in the natural deduction system. So I'll not take much time to explain it. But again, single lines, proof rules, double lines, refutation rules, two kinds of assumptions. And that's basically it. So a base is still a collection of rules of this sort. An extension of a base is still the proof-theoretical notion. Now, we do have to define two different drivability notions. And we have a drivability notion, so the turnstile with the plus sign, and one with the minus sign. So I will often just refer to these as like proofs and refutations, proofs being the plus sign and refutation being the minus sign. So the definition is still very similar to what I showed you before. The only difference here is that this sign is basically determined by what is the last rule applied. So if the derivation here showing P from these assumptions, if the derivation ends with a single line, then, well, it's a proof rule. And then we have the positive sign on turnstile. And if it ended with a double line, so a refutation rule, we have the negative, the minus sign on the turnstile. And so an example again, consider these two rules. This is a very straightforward adaptation of the example that I showed you before, but nonetheless, I think it's nice to show it. So figure you have these two rules in the base B. So we have one rule, for instance, which lets you refute Q from proof assumption P and no contra assumptions. And then you have this other rule too, where you can prove S from no proof assumptions and the contra assumption Q, no proof assumptions and contra assumption R. And we can actually build this derivation here, where we use the first rule to refute Q. And then we use this as kind of a contra assumption. And then we apply rule 2 and we prove the atom S. And so we have a derivation showing that from the assumption P and the contra assumption R, we can derive S, positive sign on the turnstile, because we ended with a single line rule. But for instance, there is no derivation showing that P can be refuted, so turnstile with minus sign in B, because there is no refutation rule for P. Okay, so semantic clauses. Now, I did say that this was going to be very heavy on notation, and I don't think I was exaggerating. So the base case is still what you would expect. So support for the base case is equivalent to derivability. Some things that I would like to call your attention to. So for instance, clause 2. If I was going back to the clauses for IPL, I would have that bottom is supported if and only if every atom is supported, well, in the base. And now here we still have this, but you can see that we need to have positive support and negative support for every atom. This is not something arbitrary at all. So when me and Victor, when we were doing this work, we were doing this until like a very advanced point with only the positive support. So bottom would be positively supported if and only if every atom would also be positively supported in the base. And the same thing for clause 5. But then at some point, we also found out that this couldn't be it, which is also something that motivated us to do those changes in the rules in the natural deduction system. So in Wansing's end-to-int, I told you that we only had like one version of some rules. And something interesting here is that when we did the split for those rules, we also get some rules which are more parallel to these semantic clauses. So here in the disjunction, which again, you need to go to the elimination rule, we also have like two parts for this clause. So we have like a part with positive support, and then repeating the same thing, but for negative support. And this is crucial to have completeness and other kind of proof theoretical results. Okay, so these are the proof clauses. And then we also have the refutation clauses, very similar. And this is more than just a similarity actually, but I'm going to talk about that in detail in a bit. So this similarity is actually a duality, in fact. So if I was to show you this first slide, after the things that I'm going to tell you right after this, you would be able to tell me what the clauses in this slide would be, because they are deeply tied. Okay, and so why am I saying this? So we do have in this natural deduction system, we do have some kind of harmony, because, okay, so we are of course in a bilateral setting. So I have told you about how we cannot reduce assertion to rejection and vice versa. But if we are looking at assertion and rejection conditions for the same connective, it makes a lot of sense that these cannot be completely arbitrary. So there must be some kind of line of thinking to choose what this should be. And in particular, we need to have that the proof and refutation conditions of a connective should be systematically opposed, in the sense that we should be able to refute a formula with or the main connective in a formula whenever we obtain refutations that are incompatible with the proof of it. And so what do we mean by this? Look, for instance, what would be a proof of the conjunction. So to prove phi and psi, we need a proof of phi and a proof of psi. So if we have refutations of phi and psi, which are incompatible with this proof condition, then we should have a refutation of the conjunction. And this is actually the case in the sense that our natural deduction rule says that we can refute phi, or rules, plural in this case. We should be able to refute phi and psi from either a refutation of phi or a refutation of psi. So there is this harmony between the proof and refutation rules in our bilateral setting. So you know that usually we have the inversion principle, and there is a coordination between introductions and eliminations. But here in the bilateral setting, we have this kind of horizontal inversion principle that tells us about coordination between proofs and refutations. But this also, so these notions can actually be like transported to the semantic realm, I guess. And we may do this by first defining a notion of duality. So first we define this for formulas. The dual of an atom is the atom itself. The dual of bottom is top. The dual of the disjunction is the conjunction of the duals, etc. And with this, we can actually also define duality for rules, which I have here. So we can extend the notion of duality from formulas to rules, doing as such. So all the green lines, which are the single lines, become double lines and vice versa. I'm looking at the one highlighted, which is the dual of a proof rule, but the dual of the refutation rule follows the same reasoning. So single lines become double lines become single lines, and in the assumptions, you just swap places. So proof assumption gamma 1 at takes place of the contra assumption and vice versa. And this is your dual rule. Well, if you have a duality of formulas and if you have duality of rules, you can actually define duality of bases. So if you have a base B, the dual of this base B is just a set of dual rules. So this is not something very out of the pocket, I mean, something very straightforward. And we can also define duality of derivations. So it is I didn't write it here because the definition is quite long, but the idea, so it's an inductive definition. Essentially, you just go to the last step of your derivation. You go to the dual formulas and dual rules there, and then you take the subderivation and you keep going to the dual in that. Either way, I don't specifically need you to know the definition of dual derivation right now. Duality of rules and bases is actually what I want you to focus on. Okay, and so I told you that we were going to look at this because we wanted to have like a sort of semantic treatment of what these harmony results mean. And so by defining these notions, we can have these two theorems or two results, purely semantic results, which are actually, so we think they are pretty neat, actually. So we have like a weak bilateral semantic harmony in which says that we have a kind of isomorphism going on. So if you have the entailment of some formula or the support of some formula in a base, and here the asterisk can be either a plus or a minus sign. The only constraint is that it needs to be like uniformly replaced. But let's say it is a plus sign to be easier to read. If we have a positive support of phi in base B, this is equivalent to having, it would be the negative support of the dual of phi in the dual base. So yeah, I mean, we can also strengthen this result to the strong bilateral semantic harmony by also adding the assumptions here. And you can see that in the second part of the if and only if, what we do is that we swap the places of the assumptions and we also go to their duals. So basically you need to like dualize everything. And so technically, what does this mean? It means that so these results tell us that we may infer the refutation conditions of a logical connective from its proof conditions. And that's why when I was showing you the semantic clauses, I told you that if I was to show you the proof clauses, you could sort of figure out what the refutation clauses would need to be. Because if we know what the dual of a certain connective is, and if we are sure of this bilateral semantic harmony, then we know that we just need to in a way like swap conditions. So proof of a conjunction would be refutation of disjunction, and these need to be corresponding in a way. And so, but also like from a philosophical standpoint, this bilateral semantic harmony amounts to preserving at the level of connectives the isomorphisms which are already present between atomic proofs and refutations. So yeah, this is the last part of the first work that we did. So just to recap, basically we took that logic to int, we changed a bit Wansing's natural deduction system, and we extended. So we proposed the base extension semantics for this logic. So we showed soundness, completeness, etc., several desirable results, and we were also able to do like a purely semantic treatment of bilateral harmony, which, yeah, I mean, I do think it is quite beautiful. Okay, so moving on to the second bit, which is basically about proofs and refutations. I'm going to start by giving you a bit of context as to how we started this second work. So into int, I don't really love how I stated this first sentence, but let's say that into int and to int star, there is nothing that prevents you from proving and refuting the same formula without giving rise to a contradiction. So there is no rule in the natural deduction system that would straight away tell you that this would be the case. And in the semantics that I just showed you, there is also nothing that tells you that proof and at the same time refutation of a formula would break something here. And so we started thinking about this because, okay, so this is okay for some settings, but there are, of course, some epistemic entities, such as mathematical proofs, where this possibility is excluded. So in doing mathematics, I really don't want to have the possibility of being able to prove and refute something, and this still being okay. So what is our proposal? The proposal is to construct a new bilateral system, which we will call BPR, for bilateral proofs and refutations, in which the joint derivability of a formula and its refutation does lead to a contradiction. And so how did we do this? Well, we take the system n to int star, and we add these interaction rules. So we call them interaction because they show the interaction or what should happen if proofs and refutations of the same formula are going on. So we add these two rules, and this is our system, BPR. I will not show again all the rules of the system because it's just like the 4 slides that I showed you before, plus these two. And so then what do we want to do with this? So we want to study the proof theory of this system, and we want to provide the base extension semantics for this logic. But also at some point, we also wanted to really analyze the paper of the role of the refutations in this system, which will be like the last part of my talk. Okay, so beginning with the proof theory. So I'm not going to show you the proofs of any of these, of course, but we showed that BPR enjoys like several desirable proof-theoretical properties. So we showed normalization, we showed subformula property. Let me say that, okay, so I will not show you the proofs, of course, because they are way too long and I don't know, detailed and weird. But let me tell you that, for instance, normalization was kind of a surprise because we thought that maybe we just had to adapt like the usual like strategies to show normalization for IPL, for instance. But then we did run into some problems, and so this proved to be like a bigger challenge than we had anticipated. But still, I mean, we did manage to do it. Then subformula is not that different from the usual strategy. But it was still interesting to see that this, not only the bilateral setting, but these interaction rules that we added to our base system, they do raise some issues when you want to study these kind of properties. Yeah, okay, so we have normalization, we have subformula property. From this subformula property for BPR, we are also able to state that n to int star also has a subformula property, which is important because one of the first things that I told you is that we did those tweaks in n2int star, because one of the things that was causing problems was a subformula property. So at the time, we didn't really do a formal proof that our system would have this property, but from this result for BPR, we are able to state this with certainty. And then, of course, we also have that BPR is consistent. Then, okay. Yeah, so this is proof theory for our system, and then we want to do the base extension semantics. So our goal is to provide the base extension semantics for logic BPR. And in order to do so, what do we need to do? So firstly, we need to change the definition of base from the start. First thing we do is that we add to the propositional base language the units bottom and top, and we need to require all bases to satisfy certain conditions. So they need to be, for instance, logical consistent, in the sense that we cannot have proofs of bottom nor refutations of top in any base or extension of any base. We need to have unit completeness, in the sense that we must have refutations of a refutation of bottom and a proof of top in every base. And then we need to have epistemic consistency, which means that every base needs to be closed under rules with this shape that you see here. So these are kind of the corresponding thing to the proof, to the interaction rules that we added to our base system, which will like close this circle to have soundness and completeness, some sound and complete semantics with respect to BPR. Okay, so we require all bases to satisfy these constraints. Let me just say that this first modification that we did regarding bottom and top, this is not something that we did in this bilateral setting because of some reason. This is actually something that appeared in work by Victor, Elaine, and Luis in an ecumenical setting. And we just, because we need to have this like consistency in bases and everything, this was a tool that they used, that we actually brought to this framework, and was crucial to prove many results. Okay, so semantics. It's very, very similar. The only difference here is that the clauses for bottom and top no longer need to be present. Why? Because now bottom and top are treated as atoms. So the semantic support within the basis of these two units is actually described by clause 1. And that's the main difference. So to refine our base extension semantics, we didn't have to change the clauses. We just needed to change the core definition of what a base is. So these are the proof clauses, the refutation clauses. Again, we didn't really need to mess with this to adapt to the incompatibility setting. And so these provide proof sound and complete semantics with respect to BPR. Okay, so so the motivation was this incompatibility thing between proofs and refutations. And again, so in 2int or in n2int, we can in general prove and refute the same formula, because there's like a sort of paraconsistent nature of this logic going on. But with the results that we have imposed on the basis, we are actually able to prove these results that I'm stating here, which was like our main motivation, but it's nice. So we managed to prove that within this setting, with this definition of base and with this definition of extension of a base, we do have that the positive support of a formula in a base implies that there cannot be the negative support of the same formula in the same base, and vice versa. So at the semantic level, proofs and refutations are incompatible. At the natural deduction, in the natural deduction system, this was already implied by the proof and refutation rules, but we also have this semantic, purely semantic theorem. And so, yeah, so BPR does offer a suitable framework for modeling epistemic entities, such as mathematical proofs, refutations, that exclude inconsistency. And this is the wrap up of part of the second work. And now I want to talk about refutability and negation. this will be like the last bit of my talk, and then we can talk if you guys want. So now let's talk about constructive falsity and refutability in BPR. So I'm going to talk about, I will begin by talking about David Nelson's work. So for those who are not familiar with it, it's fine. I will just give you like a very brief overview. So David Nelson, in his work, he proposed like an alternative to, well, to intuitionistic logics, but to the usual constructive notion of negation. And so he distinguishes between, firstly, this usual constructive notion, which I'm going to be referring to as weak negation, which can be demonstrated by providing a procedure that transforms construction of the object into a construction of a contradiction. This is the classic negation sign and can be, is usually abbreviated by, so negation of phi is phi implies bottom. So describing this construction of contradiction, right? And then Nelson talked about this strong negation thing, which I'm going to denote by this tilde sign. And you can prove the strong negation of phi by proving, by directly producing an object which witnesses falsity of the statement. So kind of a counterexample, right? And well, naturally, if you have a counterexample, so something that witnesses falsity, you can of course use this to prove weak negation, so to construct a contradiction, but you cannot do this the other way around. Okay, so why am I talking about this? Because when we were wrapping up our first paper and going to start the second one, and we began thinking about this proof and refutation incompatibility, well, Victor actually thought that, well, this seems very similar to some of the stuff that I read about Nelson's negation. And so we wanted to really understand, like, what is the logic that we are talking about, and in what sense does it relate to these stronger notions of negation. And so we have this distinction between these two. So this is just like the overview. And I actually have like an example here. So take this statement. So I'm talking here about universal statements. For instance, all even integers are divisible by 4. I have here like how I would write this with these two predicates, even and div4. And I can prove the strong negation of this formula by giving a witness. I chose n equals 2. So n is even, because it can be written as 2k, right? So 2 is 2 plus 2 times 1, so it's even. However, 4 does not divide n, because in particular, so for my case, n 2 divided by 4 would be 1/2, and this is not an integer, so 2 is not divisible by 4. So we have a witness to the falsity of the universal statement, and we could, of course, like also use this witness to build a contradiction. So if I instantiate this with n equals 2, I would have that even 2 is evaluated as true, but then divisible by 4 would not be true, and so we would have like falsum. Right. And so now we're going to start going towards the bilateral setting. So as Wansing himself suggests, we can actually associate this concept of strong negation with disprovability or refutability, if you want. So what is this association that we can make? So it makes sense in the sense that proving strong negation really amounts to giving witness and proving it directly. The same way that in the bilateral setting, refutations or disproofs should be shown directly and not by reducing them to something where they do not figure. And so we have this kind of relation. So the disprovability of phi is equivalent to the provability of strong negation of phi, and vice versa. And so these ideas about strong negation, etc., were formalized by Nelson through his systems N3 and then N4, N4 being a paraconsistent variant of N3. And so here we have some kind of hint that these have a parallel with the bilateral systems which we have been analyzing. N4 is so the paraconsistent case would be parallel to int, and then N3 maybe is parallel in some way to BPR. And by looking at this with more attention, we do have like a very strong evidence of this. So in BPR, we still have like a very strong tie between the strong negation operator and the notion of refutability, in the sense that if we have a refutation of phi, or if we have like the negative support of phi in base B, this is equivalent to having the positive support of its strong negation. And if we have the negative support of the strong negation in a base, this is also equivalent to having the positive support of the formula itself. So this is something, this is nice to have this tie between refutation and a strong negation, but moreover, we also have the relation between the strong negation and the weak, or I don't know, usual notion of negation, in the sense that in BPR, from a proof or of a refutation of phi, sorry, the strong negation of phi, which we now know is equivalent to the refutation of phi, we can show that phi implies bottom, so negation of phi, which was not the case in int, because you see that the derivation that I'm showing you here needs to use the proof and refutation rule, the interaction rule, which are not present in the base int system. And also we have that the other direction does not hold, so weak falsity. So weak falsity does not imply strong falsity. And I have this example here that witnessed to this fact. So if you take this base, this is not well formatted, I'm sorry, but this rule in the base should be that from a proof of P, you can prove bottom. If you have a base with just this rule, you can show that in this base, P implies bottom is positively supported, but then we cannot refute P. That is, we cannot prove strong negation of P. And yeah, so this was the analysis that we did between our system BPR and Nelson's notion of strong negation. We have like a very strong correspondence here, which basically like confirmed the suspicions that we had when we started this work. And yeah, let me just make some concluding remarks and then I'll wrap up. I think I'm quite on time. We'll have like 10 minutes for questions. So wrapping up, I'll just go over like everything I've told you about today. So what did we do in the course of this talk? Firstly, we saw how to extend base extension semantics to the bilateral setting. How did we do this? We allowed both proof and refutation rules in bases. And this was essentially what we needed to change to have this framework working for us. We also got out of this a purely semantic characterization of bilateral harmony. We had those two very neat results about weak bilateral semantic harmony and a strong version. Then we wanted to refine this to cover settings where we would have incompatibility between proofs and refutations. So we advanced a form of bilateralism in which proofs and refutations are treated as distinct but mutually incompatible. And so maybe I did not stress this enough, but still in this incompatibility setting, we have that proofs and refutations are still not the same act. So we still have like proper bilateralism going on, although we have incompatibility. We also saw how to modify the notion of base to get a semantics for this logic and a semantic result stating this incompatibility. And then at last, we saw how this resulting logic is intimately connected with Nelson's work and Nelson's concept of constructive or strong falsity, and how the logic is suitable for the formalization of mathematical strong falsity. And yeah, so we do have some ideas on what we could do after. It should have to do with sequence. So for int, Sarayan has very nice work on this about the cut-free sequence calculus. But maybe we would like to investigate how to extend this to our incompatibility setting. This is something that is in our plans. And yeah, I mean, I have some references here, very few of them, but these are like the main ones that I selected to bring to the talk. And yeah, that's it. Thank you so much for listening to me.